Welcome to first semester organic chemistry. Today I'm going to begin an introduction of organic chemistry, and we're going to focus on the first chapter of the Carey 11th edition. All of these lectures have a similar introductory slide. This slide tells you the title of today's lecture as well as which sections in the textbook this lecture represents. You're welcome to read these sections in advance or afterwards. I am going to ask you to work through all of the textbook problems that are embedded within these sections. Additionally, I also have a list of learning objectives. They're phrased in kind of this awkward statement, the learner will, and that's just for my own organization. But at the end of today's lecture, the learner will be able to do the things that I've identified in the first lecture slide. Let's talk about a few of the things that you should know walking into this class. First of all, this is a periodic table. I have deleted the symbols of the first 20 elements of the periodic table to give you an opportunity to practice filling these in. You should know what these first 20 elements are without a periodic table. There's also a few other elements that we'll talk about from time to time. The halogens, which is this column right here, fluorine, chlorine, bromine, and iodine. There are also some other nonmetals that show up from time to time, arsenic, selenium, and tellurium, but they are very highly toxic, and we avoid them in the laboratory, as well as the noble gases, helium, neon, argon, krypton, xenon, which show up from time to time. For the most part, though, your world of organic chemistry consists of hydrogen, oxygen, nitrogen, carbon, and the halogens. We abbreviate the halogens simply as the letter X, and so we often describe organic chemistry as the study of HONC X, where HONC is HONC, hydrogen, oxygen, nitrogen, carbon, and the X refers to the two most common halogens that we care about, which are chlorine and bromine. Hopefully during general chemistry you also gain some familiarity with the oxygen-containing polyatomic ions. The most important column in this particular table is the column that I refer to as the 8 ions. Not the number 8, but those that end in the letters ATE. For example, this is phosphate, sulfate, carbonate, nitrate, chlorate, and bromate. I often refer to these as the 5 polyatomic ions because chlorate and bromate are in many ways interchangeable. They're halogenates, but there's technically 6. There is not a lot of consistency between the charges of these 8 ions, of these ATE ions, or the number of oxygens on these ATE ions. Notice that it can have anywhere from 3 to 4 oxygens, and the charge can be anywhere from -1 to -3. So unfortunately, you do need to memorize this particular column. But once you understand this column, then you should be able to put together all other columns on this table. Related to the ATE ions, the 8 ions are the ite ions. And if you look at the 8 column versus the ite column, what you should notice is the only thing that changes is the number of oxygens. So phosphate has 4 oxygens, phosphite has 3 oxygens, and that pattern is the same for every one of these. Carbonate has 3 oxygens. Carbonite is not actually stable and doesn't truly exist, but if it did, it would have 2 oxygens. So this table is about a pattern, not necessarily about ions that truly exist. We will see nitrite show up in the context of this course. We'll talk quite a bit about sulfite. If you continue to take oxygens away, then you have the hypoite ions, and these become less and less real. In other words, the probability that they exist at all starts to drop off as we move away from the 8 ions. And I'm not sure which of these actually exist. I do know that hypochlorite and hypobromite exist. If instead we add oxygens, we also start to come up with some names and structures of ions that may not truly exist or be stable in the laboratory. But the pattern is what I'm trying to illustrate here. If you add additional oxygens, then instead of ending in 8, it ends in per8. And so we have perchlorate and perbromate are 2 ions that I know exist. Hopefully now you see the pattern between the first column, the third column, the fifth column, and the seventh column. There is also a pattern with the acid version of these polyatomic ions. If you take the ion as it stands, so phosphate, and you add the number of hydrogens that correspond to the negative charge, so 3 in the case of phosphate, then you end up with an ic acid. So all of the 8 ions give rise to the ic acids by keeping the number of oxygens constant, 4 and 4 here, but adding the number of hydrogens that corresponds to the negative charge. So if you know that carbonate is CO3 with a -2 charge, you should be able to tell me that carbonic acid is H2CO3, because knowing that carbonate is 3 oxygens with a -2 charge, and the corresponding ic acid simply has enough hydrogens to cancel the -2 charge, you can predict that it would be H2CO3. The OUS acids, the US acids, are the same relationship that we saw with ate and ic acids, but now with ite and US acids. So for example, sulfite is SO3 2-, sulfurous acid is H2SO3. And so this table is based on a pattern, and the only thing that hopefully you have to memorize are the names, the number of oxygens, and the charges of these 8 ions right here. Much of organic chemistry requires us to look specifically at the Lewis structure of compounds. So here I have 5 of the ATE ions that you need to memorize. There's sulfate, carbonate, nitrate, phosphate, and chlorate. If you want to change that to bromate, you can just take the chlorine and change it out for bromine. Oops, the hotkey is not working for me here. I can just type in Br. The structure is the same for chlorate and bromate, and that's why those two are kind of lumped together as a single unit of content that you need to know or memorize. Notice that I have placed individual negative charges on individual oxygen atoms, and hopefully now you can appreciate that if I want to convert sulfate into sulfuric acid, then let me copy and paste the base structure of sulfate. The tool that I'm using is called ChemDraw. It is available to students in my class, but I would discourage you from getting used to it right away. Once you give me a week or so, and then if you think you want to use it, then talk to me in class and I'll help you figure out how to do that. So if you want to convert sulfate into sulfuric acid, then everywhere there's a negative charge, you simply replace that with a hydrogen. Now if I delete this negative charge, ChemDraw will automatically put a hydrogen there, and it's actually the lone pair of the oxygen that's going to bond to the hydrogen. So that's why the lone pair now becomes a bond to a hydrogen and the negative charge goes away. Let me show you more explicitly what that looks like. Here's the oxygen now bound to a hydrogen. This oxygen is bound to a hydrogen. This is the Lewis structure for sulfuric acid. You can do the same thing with carbonic acid. In fact, I would encourage you to pause the video and to try to draw a Lewis structure of carbonic acid based on knowing the structure of carbonate. Then restart the video and see how you did. All right, I'm just going to go ahead and do this. Hopefully you paused this, or at the very least thought about what it would look like in your head. It is okay generally to just leave the hydrogen connected to the oxygen, but I want to try to today to make sure that we talk about individual bonds. So this is the Lewis structure for carbonic acid. I'm not going to walk through the rest of these right now, but you could continue to turn all of these into acids. Nitric acid is the only one that's tricky. Notice that there is a positive charge on the nitrogen. That actually offsets one of the negative charges on the oxygen. And this thing has a net overall charge of -1, because a minus plus a positive plus a minus gives you a -1. And only one of these oxygens ends up picking up a hydrogen. So nitric acid actually looks like this right here. And it doesn't matter which oxygen you put the hydrogen on. Now let's practice drawing some Lewis structures. Let's start off with formaldehyde. Formaldehyde may not be a compound that you're familiar with, and that's okay. The molecular formula of formaldehyde is H2CO. So it has 2 hydrogens, a carbon, and an oxygen. Generally, you place the least electronegative element in the center of the compound. That would be hydrogen, but hydrogen can't go in the center of the compound because it only makes one bond. So we put carbon in the middle. This structure is not correct because we have not yet accounted for all the valence electrons. The number of valence electrons is predictable based on the organization of the periodic table. Let's go back to a functioning periodic table with all the elements added in. The column that the element exists in tells us how many valence electrons it has. Things in the first column have one valence electron. Things in the fourth column, so we jump across the middle here, we go 1, 2, and then this is 3. Use the Roman numerals here, 3A, 4A, 5A, 6A, 7A, 8A. Those tell us how many valence electrons these compounds have. Hydrogen has 1, carbon has 4 valence electrons, and oxygen has 6. Knowing that, we go back. If hydrogen has 1, and there are 2 of them, carbon has 4, and oxygen has 6, that's a total of 12 valence electrons that I need to add to this compound. Each of these lines represents a bond or a shared pair of electrons. So of the 12 valence electrons that I have, I've already spent 6 of them. 2 here, 2 here, and 2 here. The remaining 6 electrons I want to give to whichever atom is the most electronegative. Electronegativity is one of the most important principles in organic chemistry. Let's go back to this. And the closer an element is to fluorine, the more electronegative it is. If you remember, electronegativity is a measurement of how hard an atom pulls on electrons. So oxygen is the second most electronegative element, which means that if there are electrons to spare, oxygen is going to pick those up. So I'm going to take all 6 of my remaining valence electrons and give them to the oxygen. Now this structure is still not correct. And the reason it's not correct is because the carbon does not have an octet. If you remember, the octet rule tells us that most elements would like 8 total electrons. The carbon has access to 2 in this bond, 2 more in this bond, and 2 in this bond for a total of 6. In order to give it 8 electrons, we actually need to take this lone pair, not away from the oxygen, but we need to share it between the oxygen and the carbon. And that's done using a double bond. So here is our Lewis structure for formaldehyde. Oops, that kind of switched up on, there we go. Formaldehyde illustrates some basic patterns that we see. I mentioned before that the most important elements to an organic chemist are hydrogen, oxygen, nitrogen, carbon, and the halogens, or HONC-X. Hydrogen typically makes 1 bond, oxygen makes 2 bonds, nitrogen makes 3 bonds, and carbon makes 4 bonds. The halogens also make 1 bond like hydrogen. So this is typically the number of bonds that we expect each of these elements to have. The hydrogen is making 1 bond in this structure. That's good. Carbon is making 4 total bonds. 1, 2, and then 3, 4 if you count the double bond. Oxygen is making 2 total bonds, but oxygen also has 2 lone pairs. So in addition to the number of bonds that elements will typically form, so we can write bonds right here. This is the expectation for bonds. There's also an expectation for lone pairs. Oops, I'm going to copy that and paste it. And we're going to call this lone pairs, or LPs. This refers to the lone pairs of electrons. And we can figure out how many lone pairs they need if we recognize that everybody needs a total of 8 electrons except for hydrogen. Hydrogen is weird in that it only wants 2 electrons. So if it has a bond and a bond contains 2 electrons, it's done. Oxygen gets 4 electrons from the 2 bonds, so it needs 2 lone pairs to get a total of 8 electrons and fulfill the octet rule. Nitrogen tends to make 3 bonds and have 1 lone pair. Carbon makes 4 bonds and has 0 lone pairs. And the tendency of a halogen is to make 1 bond and have 3 lone pairs. These are referred to as the HONC-X rules. They're not absolute. They get broken all the time, but they allow us to quickly start to draw chemical structures based on expecting a certain number of bonds and lone pairs for the elements that are most commonly used in organic chemistry. Let's go back and look at a couple of these structures, keeping in mind those HONC-X rules. According to the HONC-X rules, hydrogen wants to make 1 bond and has 0 lone pairs. And that's true for the only 2 hydrogens on this slide. There are a lot of oxygens on this slide. The oxygens want to make 2 bonds and have 2 lone pairs. What you'll notice is that the oxygens that follow that rule and have 2 bonds and 2 lone pairs do not have a formal charge. So this oxygen up here, 2 bonds, 2 lone pairs, no formal charge. Same is true of this oxygen and that oxygen and all the other oxygens down here on sulfuric acid. When the oxygens do not follow the Honk-X rules, that's when they end up with a negative formal charge. They could also have a positive formal charge, so the safest thing to say is if an element doesn't follow the Honk-X rules, they're going to end up with some type of formal charge. We saw for the Honk-X rules for nitrogen that we expect nitrogen to make 3 bonds and have 1 lone pair. But in this structure right here, the nitrogen is making 4 bonds and has 0 lone pairs, and therefore it ends up with a formal charge of +1. We'll talk about formal charge calculations in a minute. For now, what I want you to understand is if you don't follow the Honk-X rules, then elements end up with formal charges. Let's see what that looks like for the amide ion. Now the molecular formula of the amide ion is NH2-. If you've never heard of the amide ion, well, welcome to the amide ion. It's pretty useful. It's a much stronger base than hydroxide, and we used to think that hydroxide was a strong base in general chemistry. It's really not that impressive. We use a lot stronger bases in organic chemistry. Based on the Honk-X rules for amide, there's really not a good way to draw this one because the amide does not follow the Honk-X rules. And the structure, the Lewis structure for the amide ion is this. Okay? It's NH2, right, with a net negative charge. The hydrogens end up with 1 bond and 0 lone pairs. That's what we expect. But the nitrogen ends up with 2 bonds and 2 lone pairs. That's not what nitrogen's supposed to do. Nitrogen's supposed to have 3 bonds and 1 lone pair. So this means that the nitrogen ends up with a formal charge. The way that we calculate formal charge, so that's not how you spell formal charge. Formal charge is equal to the number of valence electrons that we expect from the periodic table minus the number of actual electrons. Electrons would be negative, like that's not there. Something like this. So the formal charge calculation is equal to the number of valence electrons that something is supposed to have minus the number of actual electrons that we've assigned it. So let's see what that looks like for nitrogen. Based on nitrogen's position on the periodic table, nitrogen should have 1, 2, 3, 4, 5 valence electrons. That's what the periodic table tells us. So formal charge for nitrogen is equal to 5 minus the number of actual electrons, which, for reasons I'll explain in just a second, is equal to lines plus dots. So lines refer to the number of bonds on the nitrogen. If you break this bond and give half of those electrons to the hydrogen and half of the nitrogen, that means that this bond tells us that nitrogen owns 1 electron from this bond. And it also owns an electron from this bond. So the lines just tell us that we're taking the bond and we're cutting it in half. Dots tell us how many individual electrons we have, not lone pairs, but actual individual electrons. And if you add up the lines and the dots that surround the nitrogen, that's equal to, I'll rewrite this one more time, formal charge is equal to 5 minus 2 plus 4. And that 2 plus 4 have to be done first. That's why I put it in parentheses. That's the way order of operations work. If you've ever gotten in a fight about that on Facebook, you wasted your time. So it's 5 minus 6, and this gives us a net -1. So that's where the -1 formal charge comes from. The next Lewis structure we want to look at is thionyl chloride. This again is not a compound that you've probably seen before, and that's okay. So thionyl chloride has a molecular formula of SOCl2. This is not an organic compound, so the Honk-X rules really aren't going to be very helpful here because the sulfur is not playing the game of organic chemistry. Organic molecules have carbon in them. This does not have carbon, so these may or may not apply. So if we don't have Honk-X rules to throw a structure up with quickly by following these rules, then we have to resort back to the more tedious method of general chemistry, where you put the least electronegative element in the middle, that's the sulfur. So I'm going to put a sulfur in the middle, and I'm going to hang everything else off of the sulfur. So we've got oxygens and, two chlorines and an oxygen are going to hang off of this thing. So there's a chlorine on that side, and an oxygen on top. The total number of valence electrons in thionyl chloride is based on the periodic table. Sulfur has 1, 2, 3, 4, 5, 6 valence electrons. Oxygen also has 6 valence electrons, and the chlorines each bring 7 valence electrons to the table. 6 plus 6 plus 7 plus 7 is 26. 6, 6 is 12. Yes. 20 is 24. No, 26. I'm right. It's 26. So I've already spent 1, 2, 3, 4, 5, 6 of those 26 electrons with those single bonds. So I have 20 electrons left to place. And I'm going to do it by putting lone pairs around the most electronegative elements until all my electrons are spent. So I've spent 6 there on the oxygen. Now it has an octet. 6 on each of the chlorines. They have their octets. And I have 2 electrons left to place, and those are going to go on the sulfur. We're going to draw Lewis structures of thionyl chloride quite often during the course, and it's always sad and I guess a testament to my poor teaching that students consistently leave the lone pair off of the sulfur when they draw the structure of this compound. It has a lone pair. Okay, so what's going on here now with this compound, and why are there red boxes on there? It's because ChemDraw doesn't like this compound. And the red boxes are actually ChemDraw's way of reminding us that this compound has formal charges. And it keeps trying to fix those by dumping hydrogens on there. So, formal charges. If you remember, the calculation for formal charge is we take the number of valence electrons that something is supposed to have, and we subtract from that the number of actual electrons that it's been assigned, which is actually just lines plus dots. So let's rewrite this formula right here, that you take the number of valence electrons from the periodic table, and you subtract the number of lines plus dots in your structure. And I don't want that superscripted. Okay, there we go. So for, it keeps messing them up. All right, let's do the sulfur now. This is really annoying. Okay, sulfur as it was. And the oxygen right here. Okay, sulfur has 6 valence electrons from the periodic table, and currently it has a total of 3 lines and 2 dots. So the 6 minus 5 gives me a positive 1. So I'm going to go ahead and dump a positive 1 formal charge on the sulfur, and you're actually going to see that the red box goes away, except for I did 2. Okay, there we go. Oxygen has 6 valence electrons as well, and I have given it a total of 7 lines and dots, so the oxygen 6 minus 7 is a negative 1. And this right here is a correct Lewis structure for thionyl chloride. But it's not the only Lewis structure for thionyl chloride. There is another concept that we introduce with the concept of Lewis structures, and this is resonance structures. Resonance structures are 2 different representations of the same molecule. They're typically shown with a double-headed arrow like this, and more technically speaking, we're supposed to put both resonance structures in brackets. This is how we, in the most tedious way possible, we talk about resonance structures. A resonance structure is the same molecular arrangement. In other words, I'm still going to have a sulfur in the middle, 2 chlorines on the bottom, and an oxygen on top. But now I'm going to take these electrons and hang them differently. Anytime you have a negative formal charge on one element and a positive formal charge on the other element, you should explore the possibility of taking a lone pair from the negatively formal charged atom and sharing it in a bond in the direction of the positive formal charge. So I'm going to take that and drop it down and make a double bond. Whoops. Oh. Okay, there we go. When I do that, it ends up taking these formal charges away. And let's check that with the math. The number of the formal charge is equal to the number of valence electrons. For the sulfur, that's 6 minus lines plus dots. There are 4 lines and 2 dots, so 6 minus a total of 6 is 0. Sulfur now has a formal charge of 0. Oxygen, we don't actually have to do this formal charge math because we can just check the Honk X rules. When oxygen has 2 bonds and 2 lone pairs, its formal charge is 0. We're good. So This resonance structure right here, which is the same general atomic arrangement, but different ways of hanging the electrons on the molecule, is a better resonance structure because we've gotten rid of the formal charges. There is one problem with this. The sulfur ends up with a total of 10 electrons. 4 electrons with the double bond, plus 2 for each of these single bonds, so that's 8, plus the lone pair tells me that sulfur has 10 electrons. The reason that the octet rule exists is because an element like neon places 8 electrons in its valence shell. It puts 2 of them in the s subshell and 1, 2, 3, 4, 5, 6 in the p subshell. Hopefully this is a concept that rings some bells of familiarity from your time in general chemistry. That neon has 2 electrons in the s subshell and 6 in the p subshell. 2 plus 6 is 8. That's the origin of the octet rule. Sulfur, in its elemental state, has 2 electrons in the s subshell and 4 electrons in the p subshell. Sulfur is in the 3rd row of the periodic table, and it has an empty d subshell. We don't actually end up parking electrons in the d subshell until we get to scandium. This is called the d block of the periodic table, and it represents those elements that are finally filling up the d subshell. The point, all elements can go above and beyond an octet if they have an empty d subshell. And those elements start in the 3rd row and down. So the octet rule is really only a hard and fast rule for the elements that do not have a d subshell, which is the 1st and 2nd row elements. But the 1st row elements don't even have a p subshell, so they don't actually follow the octet rule. Lithium and beryllium can't pick up the 8 electrons they need, so they don't actually follow the octet rule. Boron is weird because it can't quite stretch to pick up 8. It actually satisfies itself with 6, so it follows the sextet rule. So the octet rule, which is the heart and soul of Lewis structure theory from your general chemistry class, truly only applies to 5 elements: carbon, nitrogen, oxygen, fluorine, and neon. Everybody else can potentially and consistently violate the octet rule. So it's not really a rule, it's more of a suggestion. Going back to our Lewis structure right here, thionyl chloride has a sulfur. The sulfur is in the 3rd row of the periodic table, and so it will expand and go beyond the octet rule in order to get rid of these formal charges. So we always use formal charges to decide which resonance structure is the best resonance structure for a given compound. The last Lewis structure I want to look at is chloric acid, and I told you earlier that chloric acid and bromic acid are related. So I can actually just use the bromic acid Lewis structure right here. Let's open up a new one, file, new document. And we're going to zoom in a tad. And we're going to dump in the bromic acid. So I just want the bromic acid. And then I'll go back and I'm going to put it all on the same document here so we can look at it with the rest of these. So this is bromic acid. Anything that is in the same column of the periodic table is interchangeable in terms of its Lewis structure. So bromine and chlorine are in the same column of the periodic table. You can just switch those out. Oxygen and sulfur are in the same column of the periodic table. And if you had a Lewis structure of this compound and we replace the oxygen for the sulfur, this is how we would show it. Because oxygen and sulfur are in the same column, they are interchangeable. Because chlorine and bromine are in the same column, they are also interchangeable. So this is the Lewis structure for chlorate. The ATE ions become the ic acids when we add a hydrogen to them. Now the hydrogen actually comes in as an ion. So I'm going to go ahead and draw this, bring this in as the H plus ion. The H plus ion sticks to the oxygen, and it does it by pulling this lone pair into a bond right here. And so this lone pair becomes a bond. I'm just kind of imagine if this was a more creative animation than what I'm doing right now. Makes a bond to the hydrogen, and in that process, everybody starts following the Honk X rules, and so the negative charge goes away. So this is the Lewis structure for chloric acid. but it's not a correct Lewis structure because the chlorine right there does not have enough electrons, I think. Let me check. So I'm going to look at the formal charge here. Formal charge of the chlorine is equal to the 7 valence electrons that the chlorine is supposed to have from the periodic table minus lines and dots. I have no dots currently drawn on that chlorine, and I have 5 lines, and so this should have a formal charge of -2. The truth is that any formal charge that is not a 0, a +1, or a -1 means that I've made an error with my structure. So this actually should have a lone pair on here. If I had done a better job in drawing my Lewis structure for originally, then I wouldn't have had this problem. But this is the correct Lewis structure for chloric acid. That means I need to go back and fix the bromic acid. I think that's the only other error made. So let's go ahead and fix that. You can double click on a ChemDraw picture in PowerPoint and it should load ChemDraw, but occasionally it crashes my entire computer. So we'll see how this goes. I'm going to go ahead and grab the lone pair tool and drop that on the bromine, and then if I close that out, it should have updated on the PowerPoint site. Good. One more practice problem for today. Let's talk more specifically about Lewis structures. We're going to have 2 resonance structures for this compound NCO with a net negative charge. This is kind of organic. I mean, it has a carbon, but typically if it's an organic compound, the carbon is going to be bound to some hydrogens. So this, I'm going to think this more is an inorganic compound, although the definition is no longer really that defined. People have tried to make it a well-defined definition and they've wasted a lot of time. So if the compound is nitrogen, carbon, and oxygen, I'm going to put the nitrogen on one side, I'll put the carbon in the middle, and I'm going to put an oxygen on the other side. Just ignore the hydrogens for the time being. That's an artifact of what ChemDraw is trying to get me to do. Okay, I need to add up my total number of valence electrons. From the periodic table, nitrogen has 5, carbon has 4, and oxygen has 6. 5 plus 4 is 9, plus 6 is 15 total valence electrons. The negative charge tells me that somehow this ion picked up an extra negative charge. So that means that it's got an extra electron, and therefore instead of 15 electrons, there's actually 16. Currently, of my 16 electrons that I have to place, I've put 2 here and 2 here. Ignore the hydrogens. So I have 16 minus the 4 electrons placed. I have 12 electrons left to put, and I'm going to put them on the most electronegative element, oxygen, 2, 4, 6. I'm going to make myself ignore that hydrogen for a second, and then I'm going to put 6 over here on the nitrogen. All right, and let's go ahead and get rid of the hydrogens on the carbon. Okay, so now this is my first attempt at a Lewis structure. I have all of the electrons accounted for, I've tied everybody together, but I am not following the octet rule. In order for carbon to follow the octet rule, it needs 2 more bonds. You can think about this like the honk X rules, although when there's negative charges, you know that it's going to be violated. So I'm going to take 1 electron pair down from the nitrogen and 1 electron pair from the oxygen and turn those into double bonds. So that will end up giving me a carbon with a total of 8 electrons. This nitrogen is the one that ChemDraw doesn't like, so you should already kind of suspect that that's the one that's going to end up with a formal charge. We can use the honk X rules to go through this pretty quickly. Carbon is supposed to have 4 bonds and 0 lone pairs. If that statement is true, and it is, then its formal charge is 0. Oxygen is supposed to have 2 bonds and 2 lone pairs, and it does, so its formal charge is 0. Nitrogen is supposed to have 3 bonds and 1 lone pair. It does not, so its formal charge is going to be not 0. If we do the math on formal charges, it's the 5 valence electrons that nitrogen is supposed to have minus the 6 lines and dots. That's a -1. And that's good because my compound originally, right, from my PowerPoint slide, told me that it had a net -1 charge, and that's what I'm drawing right here. So this right here is a potential structure for the compound. But it's not the only structure. I could have drawn a resonance structure for this compound where I'm going to take one of these lone pairs off of the nitrogen and drop it down to make a triple bond. So I'm going to pull it down and make a triple bond between the nitrogen and the carbon. If I stopped there and that's all I did, the carbon would have 5 bonds. That's a no-no. Carbon can't go above the octet rule. So if I pull a lone pair down to make a triple bond, that means that one of these bonds has to kick over to the oxygen. And so this will end up producing, let's draw this one more time. Get rid of that. I'm going to put the negative charge off to the side. That lone pair is gone. And now I have a triple bond between the carbon and the nitrogen on this side, and I should have a single bond between the carbon and oxygen on the other side, and there is a lone pair. Based on Honk X rules, nitrogen's good, carbon's good, oxygen is the one that's in violation, so now that's where my negative charge is. So these right here represent my 2 resonance structures. Resonance structures are double-headed arrows. And if we're being as tedious as chemists like to be, we also take resonance structures and put them in brackets. So here is my correct representation of resonance structures. Now, the question is, which of these is better? Because they're not the same. When the negative formal charge is on one atom versus another, the molecule is going to have a preference. And generally speaking, the negative formal charge will end up on the more electronegative species. So that means that this compound right here is my better resonance structure. This is better because negative formal charge on more electronegative atom. And we're going to dump that back on my PowerPoint. Just taking notes here for you. All right, that's as much as I was planning on covering today. Tomorrow we're going to talk about this. So let's go back and review the learning objectives right here. The learner will predict the number of valence electrons on S and P block elements. That was based on counting over the columns on the periodic table. We will predict ionic charge and know when ionic charges are not feasible. We didn't actually do that, so let's take a look at that right now. Ionic charge is how many electrons an atom has to gain or lose to be like the nearest noble gas. So fluorine, in order to be like neon, has to pick up 1 electron to become like the nearest noble gas. If you pick up an electron, you become a negative charge. Sodium the closest noble gas to sodium is neon, so it would lose an electron to be like neon. And if you lose an electron, you become positive. So sodium takes on a positive 1 charge. It is not reasonable for sodium to take on a negative 1 charge under most situations. We didn't expect sodium to do that. We'll draw correct Lewis structures. We did that today. I have quite a few examples of different Lewis structures that we drew today using both the Honk X rules and the general way of doing it in general chemistry, where you put the least electronegative element in the middle and then count up all your valence electrons. We'll calculate formal charges for any atom in a molecule. I went ahead and left the equation for formal charge. It's the number of valence electrons that we expect from the periodic table minus lines and dots. And we did a couple examples of that. And draw all possible resonance structures for any given compound. That's a pretty tedious exercise, so usually I will be more specific and just tell you the number of resonance structures that I want you to draw. So today we looked at 2 different resonance structures for this compound, and we actually made a choice about which resonance structure was preferable based on the rules of electronegativity. Your homework assignment for today. Okay? Right here. Now the homework assignment is broken up for the entire chapter, so it's a little difficult for you to know how far to go on a given homework assignment. So what I would encourage you to do is to look at the sections in today's lecture, and these textbook problems right here are required. You're going to need to go ahead and complete these and turn them in. 1 through 42 are all of the textbook problems that are embedded within the reading. You have a solutions manual if you get stuck on those. So I would go ahead and start on the textbook problems that correspond to the problems that we looked at specifically in the sections that I mentioned on the PowerPoint slide today. This particular homework assignment is a little longer than normal. It's because I got a lot more words on there. So you should be able to go ahead and complete questions 1 through, yep, right here. Nope, 1 through 9. If you finish the textbook problems and are still motivated, then you definitely want to try to get 1 through 9 done on these additional problems that I have for you.